Okay, so now we're going to find parametric equations. There are infinitely many pairs of parametric equations that can represent the same plane curve. So we're going to find like the easiest set that there is out there. One set of parametric equations for the plane curve defined by y equals f of x is to simply let x be equal to t, and then y is equal to f of t, in which t is in the domain of f. That is the easiest thing we do in math for like the rest of your math. So all we're going to do is define x to be equal to t, and then y is exactly what we had up here, except we're going to plug t in for x. Y equals 2t minus 5. And that's it. Don't make it hard. And we'll do the same thing for our other example. We'll let x be equal to t, and then y is going to be t squared minus 3. Questions, anybody? An application of parametric equations is projectile motion. We frequently use parametric equations to represent the path of a moving object because we can discuss both the horizontal change and the vertical change as time goes past. So if t represents time, parametric equations give the location of a moving object and tell when the object is located at each of its positions. Rectangular equations tell where the moving object is located, but does not reveal when the object is in a particular position. So that's why parametric equations can be so much better. They give us more information. When an object is propelled upward in an inclination theta to the horizontal with an initial speed of v sub 0, the resulting motion is called projectile motion. Here we have our formulas for projectile motion. X equals v sub 0 cosine theta times t, and then y equals negative 1/2 gt squared plus v sub 0 sine of theta times t plus h. Now g represents gravity, so we're going to use 32 feet per second when we are in US units and 9.8 meters per second when we are in metric. So here goes. Suppose Jim hits a golf ball with an initial velocity of 100 feet per second and an angle of 30 degrees to the horizontal. First thing we want to do is find the parametric equations that describe the position of the ball as a function of time. So we'll be using those formulas that we just had for x and y. So x is equal to v sub 0 cosine theta times t, and we're just plugging in. Our v sub 0 is 150, our theta is 30. Don't forget your variable t, and then we just clean it up. Cosine of 30 degrees, square root of 3 over 2. So this can simplify to x being 75 square root of 3 times t. Any questions on the x? All right, so then for y, that's the more complicated formula. Negative 1/2 gt squared plus v sub 0 sine of t plus h. Since they told us that our velocity was feet per second, we know that we're in US units. So when we plug in for g, we're going to be using 32. And then what's our h? H is the height off the ground. Where's a golf ball usually at? usually on the ground when we hit it. So the height here is going to be 0. And now we just clean this up. That's going to be negative 16t squared. This is 150 times a half t. Y equals negative 16t squared plus 75t. Any questions on coming up with the equation? All right, great. We're going to use these equations to then answer some questions. The first question is, how long is the ball in the air? Oh, we need to determine whether we're going to use our x or our y equation to answer this question. Anybody have any suggestions?
The y.
Tell me why you want to use the y.
Weren't we finding more of how high it goes and like y? Like the height.
Right. So x represents the linear distance traveled, like the horizontal distance, and y represents our vertical distance. And if the ball's in the air, well, then it's up off the ground, so it has that vertical distance to it. Well, that being said, then what do I do with? So I'm going to use the y equation, but what's my setup? What do I do with that y equation? And anybody can chime in on that.
Yeah, I'm not.
Yeah.
Would you factor out a t?
Well, so back up. What's your step? What are you doing first? You're right. You're just, halfway through it. So if we want to know how long the ball is in the air, we need to know like the starting and stopping point of being in the air. And it's when it starts being in the air, like just before it's in the air, the height is 0 because it's on the ground. And then when it stops being in the air, the height is, well, back to 0. So what we're going to do is we're going to take that y equation and we're going to set it equal to 0. Yes, Olivia? During our solving process, we can factor out a t, but we got to get our equation set up first. Now, solving this quadratic, we can factor out a t. And then using our 0 product property, we get t to be equal to 0 and t to be equal to 75 over 16. Do both of these answers make sense for the context of our application? If I want to know how long it's in the air, does 0 make sense?
No.
No, because that's before I even hit it. So this one doesn't make sense. And I've never said, oh man, that took 75 over 16 seconds. So let's get it to, a decimal. We'll round it to the nearest hundredth. 4.69 seconds. Questions on part B? All right, then. Part C says, when is the ball at its maximum height? Determine the maximum height of the ball. So when is it at its max height, and what is that max height? Which equation are we going to use, the x or the y?
The x.
Tell me why. So it's talking about the height, right? So is height usually a horizontal thing or a vertical thing?
Vertical.
A vertical thing. So that tells us that we should be using our y equation. Notice that our y equation is a quadratic. And it's a quadratic with a negative leading coefficient. So that tells us that the graph of this quadratic would be a parabola that's pointing down. Where does the maximum of that occur?
That'd be halfway.
Can I get a vocab word?
I can't think of it.
Starts with a V.
Vertex.
Right here
Vertex.
at the vertex, right? So what we need to do is we need to find the vertex of our parabola, and that's where the maximum height will be. Now, the first part of it says when, so we're looking for a t. Now, typically for vertex, we have the formula x equals negative b over 2a, but in this equation, our variable is not x, it's t. So our t value is going to be negative b over 2a, and that'll give us the when. So negative 75 over 2 times negative 16. That is not a nice number, so we're rounding to the nearest thousandth. Actually, no, I'm going to keep the fraction. Oh, God. Okay, I'm going to do two things. First, I'm going to get the fraction. Then I'm going to round it to the nearest thousandth. But when I put it in to find the corresponding y value for the second part of the question, I'm going to use the fraction so that I get the most correct answer for the second part. All right, so we get 75 over 32, which is 2.344 seconds. So that's the when. Does it reach its max height? The second part, determine the max height, so then that's just the y value.
I have a question about determining the time.
Yep. And the answer
Um,
to your question.
So you can divide the.
Yep, I'm gonna get to that in just one sec.
Okay.
Well, whatever. I guess I could jump to it right now. So go ahead, Eric, say what you were gonna say.
Well, I was just wondering if you could divide the full length of the time that it's in the air by 2 and get your answer that way.
So yes, you can, as long as the object starting and stopping point is like the same height. If you are on a cliff and so your height is starting here and then they throw something in a valley, you can do.
Okay, that makes sense.
The only time that you can just cut the total time in half for the max time is if it's starting and stopping at the same height. Everybody good on that? So the max heights we're plugging in, and like I said, I'm going to plug in the 75 over 32 rather than a rounded answer. But in my notes, I plugged in a rounded answer, so I want somebody else to give me what the exact answer is here. Well, rounded to the nearest thousandth. I don't know if it's going to be off from what I have written in my notes.
I got 87.89.
Sounds good to me. That's what I have in my notes anyways. So great. Questions at all? All
Well, we
right.
need to have that formula memorized for a test.
Well, they're all open book now, aren't they? So you guys don't have to memorize anything anymore. Aren't you lucky? But no, even if we were in class, I would not make you memorize this. I imagine your physics instructors will, but I don't know it, so I won't make you memorize. Yeah, of course you got to know x equals negative b over 2a. Well, but again, I guess all the tests are open book now, so. Last part, we want to determine the distance the ball traveled while in flight, round to the nearest 1,000. So how about we figure that out?
Would we use the X formula?
So we want to use the x formula because we're talking about distance, and like when they say that somebody hits a baseball or a golf ball so many feet, they're not like mapping the vertical height like this. We're talking about just this distance right here, which is horizontal. So yeah, we want to use our x equation here. Just 75 square root of 3 times t. All right, well, I'm trying to find x, so that means I need some kind of t to plug in here. What t should I plug in?
Would that be the overall time? Like,
Yeah, it's
or
going to be the overall time traveled, right? We established in part B that the golf ball's in the air for 4.69 seconds, so all we're doing is plug in 4.69 seconds in. That's 75 square root of 3 times 4 point. Oh, geez, I didn't go to the nearest thousand. Did what is it, 69 something?
4.688.
Thanks. And what do we get?
I got 608.9. Well, I guess 609 technically.
We're going to the nearest
Is it?
thousand.
Yeah, because it's 608.989. I mean, yeah, I guess it would just be
So we
that.
got to put 3 zeros there. You said
Yeah.
so we're rounding up to 609.
Yeah.
And our unit is feet. And remember, if you ever hear them talk about golf, they talk in yards. So 600 feet is not the same as 600 yards. That is not amazing. Questions, anybody? All right. Well, that is the end of what is that? Chapter 9. Any questions at all on any of the conics or parametric equations? All right, well, then we are going to shift into chapter 11, which is basically chapter 1 in calculus. We're going to talk about, for quite a while, we're going to talk about limits. We'll also talk about the official definition of continuity here. So back when we introduced asymptotes for rational functions, right, we know that an asymptote is a line that our graph gets really, really, really close to, but never ever touches. And just to refresh any of you who actually took college algebra with me, I want to bring up a diagram that we did. So when I kind of first introduced asymptotes in college algebra, we looked at the graph of f of x equals 1 over x, and we talked about, you know, what happens if it got really, really, really close to something. Well, I mentioned at that time that it was called the limit, and we would save it for calculus, and it would have some new notation to it. Well, here we are, ready to talk about limits. Sorry, I hate when it does this to me. All right. So let's consider the function f of x equals x squared minus x minus 6 over x plus 2. Now we know that this function is undefined at -2 because we have it. -2 creates a 0 in the denominator, but sometimes we want to know what happens is we get really, really, really close to that undefined value. Now, in this example, it is not a vertical asymptote because if we factor, right, we see that we actually have a hole at -2 and not a vertical asymptote. So here, this is an XY chart, but I'm going horizontal with it. So here are my X values. So what I did is I want to see, well, what's happening is we get really, really close to -2, which is my undefined value. And then I have the corresponding Y values below it. So we see as f of x approaches, as x approaches -2 from the left, we see that our Y values are getting closer and closer and closer to -5. And then similarly, if we look on this side, as the x values approach -2 from the right, the Y values again are getting closer and closer to -5. So here is our limit notation. Suppose that f is a function defined on some open interval containing the number a. And remember that the word open interval means that the endpoints are not included. We're talking about parentheses on either end, not including the end. The function f may or may not be defined at this number a. So here's our limit notation right here. And the way we read this is the limit as x approaches a of f of x is equal to L. All the limit means and what this notation is as our x value gets really, really close to whatever this number down here is, our y value gets really, really close to whatever L is. Any questions kind of just on the notation? And maybe we need to do some before you have questions. Okay, so we're going to find limits using tools. Here, we want to find the limit as x approaches 4 of 1 over x minus 3. I know our function's defined at 4. It's undefined at 3. I did not make a typo here. We can find the limit even if a function is defined at a particular a value. It just up here it says it may or may not be defined at a. So in this one, it just happens to be defined at a. All right, well, we just need to plug in to our function each of these x values. So I'm just going to pause and give you guys a minute to fill in your table. All right, so let's get some values plugged into our table. So what is our y value with our x value of 3.5?
I got 2.
All right, how about the next one?
1.11
Okay,
and 1.01.
great.
1. 0.99. 0.909. And then 0.6 repeating.
All right, so if we take a look at it and we look at what's happening as we approach 4 from both the left and the right, what are we noticing is happening at 4? Well, we're getting closer and closer to 1. So that's what our limit is. Questions, anybody? All right, let's look at another one. Oh, this one's worse. The limit as x approaches 0 of sine of x squared over x. Now, this time we see that our function is undefined at the x value we are approaching. All right, we're undefined at 0. So again, we just want to plug these numbers into our function and get the corresponding y value and see if we're approaching the same number from both sides. And I'm filling them in this time. All right. So those are the numbers that I got. If we take a look from the left side as x is approaching 0 from the left, our y value is getting close to what number?
0.
F of x is approaching 0. And then if we look from the other direction, our y value, again, getting smaller and smaller and smaller, it is approaching 0. So because we're approaching 0 from both sides, that means that the limit as x approaches 0 of sine of x squared over x is equal to 0. Let's check out one that is a piecewise function. We want to find the limit as x approaches 0 of f of x, where f of x is the piecewise function, x plus 1, when x is strictly less than 0, and 3x plus 2, when x is greater than or equal to 0. So we're approaching 0, but you'll notice that our piecewise function is split up over 0. So as we approach 0 from the left-hand side, we're technically less than 0. So we'll be using the x plus 1 to answer those ones. And then when we're approaching 0 from the right side, we're greater than 0. So we'll be using the 3x plus 2 to answer those ones. And we'll plug in here. So as we're approaching 0 from the left, those are my numbers. So what would you say f of x is approaching over here?
1.
It's getting closer and closer to 1. I agree. And I will do the same thing on the other side. But remember, we're using this other function. We're going to be using 3x plus 2 to fill these ones in. So taking a look at what's happening as x approaches 0 from the right side, what is our y value approaching?
2.
This time it's approaching 2. So for the first time, we have different answers for whether we're approaching from the left or the right. Like here they were both 0. Here we didn't write it, but it was they were both approaching 1. When you don't get the same number as you approach from the left and the right, that means that the limit does not exist. I'm trying to figure out how I want to write this. Since we got two different answers when approaching from each side. The limit as x approaches 0 of f of x does not exist. This actually happens relatively often, that a limit does not exist. So we'll even shorthand it. This does not exist is just DNE because it comes up frequently enough. Any questions on finding the limit from a table? You really just plug in. We don't actually look at necessarily what this value is. Sometimes it's defined, sometimes it's not. Here it was defined at 2, but really we're not looking at that x value. We just want to know when we get really, really, really close to that x value. So you notice that we were looking at what's happening as we approach from the left, what's happening when we approach from the right. Well, these are called left and right hand limits, and the notation is just a little bit different. So this first one here is our notation for left hand limits. And you'll notice that the only difference here is that we have the little, like, it looks almost like an exponent of a negative above the a for our left-hand limit. And when we were in college algebra and we did that kind of intro problem, we did the same thing, right? We talked about as x approached 0 from the negative side or the left side, or x approached 0 from the right or the positive side. It's that same kind of notation that we're doing here. So here we have the limit as x approaches a from the negative side or the left side of f of x. equals L. This is called the left-hand side limit. This means that as x gets closer to a but remains less than a, the corresponding values of f of x get closer to L. And then we have a similar thing with our right-hand limit. So here we got the little plus sign. Here we had the minus. Here we got the little plus sign. It's read the limit as x approaches a from the right of f of x equals the number L. It's called the right-hand limit. So we're just approaching a from the positive side, the right side. This means that as x gets closer to a but remains greater than a, the corresponding values of f of x get closer to L. It is a fact that the limit as x approaches a of f of x is equal to L if and only if both the left and right hand limits equal that number L as well. If your left and right hand limits equal different numbers, so that's our notation there. The limit as x approaches a from the left equals L, while the limit as x approaches a from the right equals m. Right? So if those two limits are not the same, then the limit as x approaches a does not exist. So the left and right hand limits have to match in order for the limit as x approaches that number in general for it to exist. So next up, what we're going to do, I'm sorry, were there any questions on that first? All right, next what we're going to do is we're going to find the limit using graphs. I think this one, I love a picture. I think this is the best way to understand what this whole idea of limits means, because we're going to progress and everything's going to turn into algebra and we're not going to have a nice picture. But I feel like this is a really good way to really understand what's going on. All right, in part A, we want to find the limit as x approaches -2 from the left. So the first thing we have to do is be able to read the notation. Everybody comfortable with the notation? All right, so in part A, we're going to follow our graph and look. We're trying to figure out what y value are we getting close to as x gets close to -2 from the left side. So what y value are we getting close to there? Anybody? Don't make it hard. I'm coming here. I'm getting close to this point right here, and the y value for that point
Would it be 1?
is going to be just 1. Now we're going to look at the limit as x approaches -2, but this time from the right side. So I'm following my graph this way, approaching -2 from the right side. What y value are we getting close to? Well, +1 again. In part C, it's asking what is the limit as x approaches -2 overall. This is where you are looking at your left and right hand limits. If they match, then our limit as x approaches -2 is just whatever that matching number is. If they don't match, then the limit does not exist. So in this case, they match, so the limit as x approaches -2 is 1. Right, our 3 dots in a triangle like that means therefore. So those two match, therefore we can conclude that the limit as x approaches -2 of f of x is 1 as well. And then in part D, they want us to find the f of -2. So that is, what is the actual point? What is the actual y value when the x value is -2? Because the limit in the x
actual value aren't necessarily the same thing. So if we go back to our graph, and now we want to find what is the actual y value when x is 2, well, the actual y value is up here where we have the closed-in circle. The actual y value is 2. So sometimes the limit and the actual value are the same, and sometimes they're not. Questions at all on that? All right, well, now we're approaching +1. So we'll start first with the left side as x approaches, I'm sorry, +1. I think I said negative. As x approaches +1 from the left, what y value are we getting close to?
2,
2. And then we look at the limit as x approaches 1 from the right. What y value are we getting close to?
2,
2 again. So both of these are 2. Part G says, what's the limit as x approaches 1? What's that going to be? Is that defined?
Yeah, won't it be 2?
It's going to be 2 because these two match. And then in part H, we want to find the actual y value when x is equal to 1. So here's where x is equal to 1. What's the actual y value?
would that be undefined?
Mm-hmm. It's going to be undefined because there's no closed circle or solid line anywhere where x is equal to 1. So we wouldn't say does not exist. We use that for the limits. We say undefined when there is not a closed circle there. Questions on that set? All right, let's do the limit as x approaches 2 now. So we're going to do left and right side of 2, and then the overall. Oh, the left side, the limit as x approaches 2 from the left, what y value are we getting close to?
1.
1. Then we want to look at the limit as x approaches 2 from the right. So that's happening up here. What y value are we getting close to?
3.
3. In part K, we want to find the limit as x approaches 2 overall. Does that limit exist?
No.
No. These don't match. Therefore, we can conclude that this limit here does not exist. And then lastly, for this set, we want to find f of 2. So what is the actual y value when x is 2?
1.
Try again. -1.
Oh, yeah, I didn't see it down there.
We're looking for the closed circle.
Yeah, that's okay.
Anybody? Questions? I mean, this is such a classic problem. Absolutely, this is going to be on your first calc exam for sure. You're going to see it on our Unit 4 exam. We're going to see it on our final exam as well. But definitely on your first calc test. All right, now we want to do the same thing with 3. So let's start with the limit as x approaches 3 from the left. So we're coming in here. That corresponding y value as we, no, that's not what I want to say. What y value are we getting close to as x approaches 3 from the left?
0.
So make sure that we're coming in from the left and then stopping before we get to 3, right? Here's where 3 is. So we're only looking at the part that is to the left. And what's that y value we're getting close to? Not 0. I think you're looking on the right side.
2.
On the left side, we're getting close to,
Would it be 2?
we're getting close to 2. Next, we want to check the limit as x approaches 3 from the right. So we're looking at this part, and what y value are we getting close to?
This is 0.
0. Will the limit as x approaches 3 in general exist?
No.
Nope, because these don't match. And then last but not least, I want to find f of 3. So what is the actual y value when x is equal to 3? So we're looking for that solid line or a filled in circle.
2.
And it's going to be 2. Questions at all? All right, so there's one more I want you guys to try, and then we'll come back. I'm actually going to try the whole breakout room thing. I haven't done that yet. First off, I want to mention that these have arrows on the end. All right. But yeah, I'm going to try this breakout feature. I've never done it before, so if I disconnect everybody, sorry, please come back in. All right, so what did you guys get for the limit as x approached -4 from the left?
-2.
2. Right, so the y value we're getting close to is -2. Then we need the limit as x approaches -4, but this time from the right. So we're looking this direction. What are we getting close to?
-2.
Great. So how about the limit then as x approaches -4? Oh, yeah, that's the right number. Since these two match, right? That limit exists and it's equal to -2. What was f of -4? The actual value?
-2.
-2. So sometimes the limit and the actual value actually are the same thing. All right, we'll do the next one, this next grouping with -2, and then I'll leave the other ones because, like Jordan said, he didn't have enough time to get through it. So you guys can get through it, and then we'll talk about it first thing on Monday. So we're looking now as we approach -2. So what's the limit from the left?
3.
3. The limit from the right?
3.
3. So our limit overall is
3.
3.
3.
And then what is f of -2?
5.
5. All right, great. So yeah, like I said, I'll leave the other half for you guys to finish up, and we'll talk about it first thing on Monday, and then we're going to proceed in this conversation of limits on Monday, and we're going to start talking about what the properties of limits are and how to find these limits algebraically, because we're not always going to have the graph. Anybody questions about anything before we leave for the day?
Nope.
I imagine all your chapter 9 stuff is going to be due Sunday night at midnight. Take home quiz and your homework, so don't forget about that. Everyone have a wonderful weekend.
Thank you, you too.
Thanks.
Bye.
Yep.
Bye.
Bye.